Okay, so we're going to do another axial displacement problem. As you can see from the diagram, we're just going to grow it a little bit in complexity or apparent complexity, because quite frankly, once we start to break this down into its bits, we'll see that it's actually quite simple. And we'll also start to streamline our procedures a little bit. We won't be quite as deliberate on every single step so that we can get a more natural flow to our problem's solutions. So in this system, we're interested in the vertical displacement at NC, which is really the bar ABC, which is an axially loaded bar. The lever BD is a bit of a distraction because it's just saying you're going to have to transfer that load of 26 kilonewtons onto the axially loaded bar and then deal with the axially loaded bar. So why don't we start there and determine what the force is at B caused by the force applied at D. And so we're going to isolate our horizontal lever. So we're going to say solve for our force at B. So we're just going to do a quick free body diagram of the horizontal member BD. I'll draw in the fulcrum, and it has a force acting down here of 26 kilonewtons and needs to be balanced by a force acting on it down here at B, force at B. And so we'll just do a quick resolution, some of the forces about the fulcrum. Set it equal to 0. We use a clockwise as positive, and that would be equal to negative FB times the distance A plus 26 kilonewtons times the distance A. So F at B is equal to 26 kilonewtons. Now it's worth noting that that's pushing down on the lever. So the lever is pushing back the other direction up on what's resisting it. So the actual force applied to the axial member AB is 26 kilonewtons acting up. So I just probably make a note of that. So force at B on vertical member is 26 kilonewtons up. So now I'm going to carry on. I'm actually going to do my free body diagram for the vertical member AB, and I'm going to do that off to the side that lines up rather nicely with it. So we'll just label that free body diagram, put on my applied loads. So we have 10 kilonewtons, and we said a load at B of 26 kilonewtons going up. And of course, we have a reaction force. So that's our reaction at A, pushing down. And of course, we can apply our statics. Let's go statics on ABC. So sum of the forces in the y direction equals 0 is equal to negative RA plus 26 kilonewtons minus 10 kilonewtons. And so RA is equal to 16 kilonewtons. So now I want to draw my axial force diagram. So we've had a couple videos out there on how to do axial force diagrams. So I'll put up a card to previous videos in case you're not completely familiar with the axial force diagram or how to create it. We're going to go ahead and create the axial force diagram, and I'll also show you how using the method of sections you can validate that. So we know that the top half AB is in compression. So in our sign convention that we use, we're going to draw that as negative. I'll draw a negative to the left in this case. So it's constant across the entire section AB because there's no forces applied between A and B. So that's going to be minus 16. I'll say compression just to be clear. And then when we take minus 16, we add 26 to that, we're going to go up to a positive 10 or positive 10. And again, it's constant between B and C because there's no forces applied. And then, of course, the 10 that's applied at the bottom brings us back to 0, and that is in tension. Now, if you very quickly wanted to do the method of sections on that without drawing out a whole bunch of small free body diagrams, whatever, quite frankly, you can just go to your larger free body diagram, draw yourself a line across it in the section that you're interested in, place your hand to take away all of one side or the other, and just add up your forces, being cognizant of the signs, and that you should come up with the value that you're showing on your free body diagram. So we can do it here for AB. We pass our line here, throw away half, and we can do it again between B and C. So we have our axial force diagram. So we know all of the internal loads between A and B. There's two different loads and two different cross sections. So they happen to line up. So we're going to have two different sections. So let's just say calculate displacement at C. And so our displacement at C is equal to the sum of P at I, L at I, E at I, A at I. And as I mentioned earlier, we have two sections. So we're just going to first deal with the section between A and B, and then we'll deal with the section between B and C, adding them up. So then between A and B, from our axial force diagram, we know we have a axial load of 16 kilonewtons. We'll put in our length of 500 millimeters. And our E then would be 200 gigapascals, and our area, as shown in the diagram, of 160 millimeters squared. And so that would be the displacement that's happening between A and B. And to that, we have to add the displacement that would happen between B and C. In this case, it's a positive 10 kilonewtons. The area is a bit smaller at 100. Oh, sorry. Then we have the length over which it's applied, which is a bit longer, 800 millimeters. And then the E is the same, 200 GPa, but we have a smaller area of 100 millimeters squared. And so when we add all of that up, we can figure out that the displacement is 0.15 millimeters. And because of the sign, we know that it is going down, which is to say that it is an overall elongation. Okay, so that answers the problem that was asked, and you can see it's actually a very, very simple problem, although there is a fair amount of sophistication that goes into creating the free body diagram using the method of sections or the graphical method to generate the axial force diagram, and then applying our displacement equation over the multiple sections. But not as difficult as perhaps the image might imply when you first look at it. It gets a little bit intimidating. So hopefully that was useful to you, and we'll see you at the next video.